Next little section is on reducing power in ASIC designs. One of the ways of doing that is to minimize activity. That could be done by automatic clock gating. If the tools can generate or infer the gating from HDL, that's probably still in its infancy to some degree. Partition the design so that minimum number of components are activated to perform each operation. That also may mean selecting a different algorithm, and as a consequence you might have better power performance. Use lowest voltage and slowest frequency necessary to reach target performance, and use pipeline and parallel architectures if possible, as we saw previously. One of the big factors, of course, would be to reduce the switching capacitance, and here it's pointed out to design efficient RTLs, so the biggest savings come from picking better hardware algorithms to reduce power and area. Floor plan units to reduce length of power-hungry global wires as well. Optimization for static power, reduce the amount of logic required for a function, so multiplex units as well. Partition design so that components can be power gated or have independent voltage supplies. And modern standard cell libraries often include low power cells, high VT cells, and low VT cells, and tools can automatically place non-critical cells to optimize for the static power. With respect to power dissipation, one of the issues is going to be possible IR drops across the power network. Here's an example of some circuitry here and the power supply rails, and basically they have parasitic capacitances and resistances associated with them, and there's two different types of power that drop that you might see, and one would be a steady state IR drop or a static power drop, just by virtue of the fact that everything is leaking on this chip, and these lines are resistive, so current flowing through it gives you an IR drop, and a dynamic IR drop as well, in which case you have devices switching, which is then pulling current, and it's also causing an IR drop because there's current flowing across the resistor. So those are kind of those two scenarios illustrated. And one of the things to note is that in this particular case, lots of capacitance associated with the power supply is probably quite a good thing. Here's a power distribution, a couple of approaches. One's a custom approach up here, or actually I guess they're all custom approaches. And here where you're just routing power and ground on two different stacked layers of metal, one VDD, one for ground, and that might be okay for low power designs with just a few levels of metal. A power grid is probably a little bit more common, where you're going to distribute power and ground all over the chip in a grid type fashion. And one scenario that you might see from a printed circuit board technology might have been dedicated VDD and ground planes, very expensive and probably not used that often. So one of the approaches again would be, in this particular case we're looking at some standard cells, or they're probably relatively simple, they all look like inverters here. So this would be our ground power rail, and this would be our VDD. And what we do, we basically will have another level of strapping and power to get there. And one of these of course is bringing VDD, and the other of course is bringing ground, and those are connected up in this kind of fashion. So you basically have these power rings around all parts of circuitry on a grid-like fashion. So a fair bit of attention would be paid to the early physical partitioning and prototyping of the design to make sure you're going to meet the power requirements. And basically that means make sure it doesn't heat up too much and doesn't dissipate too much power, because the other problems of course are going to be associated with, as we said before, the IR drops in the power supply rails. This is an example of an ASIC backend tool that I think it's Synopsys, I don't know for sure, sort of showing a picture of a piece of the layout, and this was some kind of a standard cell environment, and it's a grid of power and ground. And there are some analysis tools in that allow you to determine, based on the activity of the underlying circuitry, sort of what would be the expected IR drops across the chip, and the consequence, once you know that, you may be able to partition it differently or place and route it differently so that perhaps that's more uniform, or at least not as severe in certain areas. Certainly there are tools that help you design for an efficient power supply and building power grid structures. One of the things to take into account here, which you may be aware of, is that in addition to trying to optimize area when you do your place and route, it also affects the energy dissipation, and there would be tools that would allow you to determine whether you're getting a nice uniform energy distribution, perhaps depending on how you laid out the design. This figure below shows what an optimization might look like. You've probably seen this before in SPICE kind of designs, where you change some parameters associated with the circuit. These are changing parameters associated with the power supply. So this picture over here sort of represents power and ground grid, and every power and ground line is the same width, Whereas over here, based on the analysis, some of these wires would be shrunk if they didn't have to carry as much current, or they would be made a little bit wider if they had to carry more current. So that's a kind of optimization that can be done once you know what the power requirements of the underlying circuitry is. Here's an example of a power grid on a 16-bit microcontroller. It's an open core design that sort of shows the power grid, and the next picture just shows it overlaid with all the standard cells which it's supplying power to. In summary of this section, well, one of the things we noted, those are fairly nice pictures, but in the case of most complex design, it's relatively complex, and certainly clock networks and circuits, as well as the power grids, are no exceptions to that rule.